Dear Professor Penrose, I was pleased to listen to the interview with you, Professor Penrose, the one posted in last days on the YouTube channel, This Is It, Maciej Kowecki. I found it interesting what you said about the different ways of mathematical thinking, the arithmetic way of thinking and the geometric way. Awareness of this issue is important, and I greatly count on your abilities in this area, your honesty and courage in openly rejecting string theory, at a time when it was still widely accepted in the scientific community and very fashionable, deserve respect, as well as your ability to admit your own mistakes and change your views, as you mentioned in the context of the cosmological constant. I fully agree with you, Professor Penrose, that constructing an elegant, beautiful, and exciting model does not automatically mean that one has constructed a realistic model, a true model, that correctly describes the real world. A spectacular example of a theory generally considered correct and significant in the scientific community, but which is in fact fundamentally flawed, is set theory, whose initiator is widely regarded as Professor Georg Cantor. I know that you are familiar with Professor Christoph Meissner, and even collaborated with him on certain issues, as you mentioned in the interview. I personally greatly appreciate Professor Meissner, not only for his intellect and scientific struggles, but also for his strong commitment to popularizing science. However, I am aware that Professor Meissner is unfortunately not aware that set theory, which currently plays a very important role in mathematics, physics, and many other areas, is a flawed theory, a false description of reality in terms of the relationships between infinite sets and elements of infinite sets. For some time now, I have been intrigued by the question of whether you, Professor Penrose, are aware of the errors in set theory. While listening to certain parts of your lecture during your visit to Poland at the end of 2016, which is available on the YouTube channel Copernicus, I find it difficult to resist the impression that you, Professor Penrose, have also fallen victim to the errors of set theory with far-reaching consequences. I analyze and demonstrate many of these errors in a working presentation titled Analysis of Mistakes in Attempts to Study Infinity, a part of which I am sending to you in English translation as an attachment to this email. One of the root causes of the errors in set theory, as well as errors in certain areas of mathematics, physics, and other fields where mathematics is used as a tool or where mathematical models serve as inspiration, is the lack of a correct understanding of fundamental mathematical objects. These include objects such as number line, or a number, for example, the number 1. Here I would like to draw your attention to this very important issue. This object is not the number 1. The object is a graphical symbolic representation of another object, a mathematical object known as the number 1. There are more objects commonly recognized and used in various circumstances as symbolic representations of the mathematical object the number 1, such as 1.01, 1.00. In many situations, these objects can practically be used interchangeably as symbolic representations of the object the number 1. Example, in arithmetic operations, 1 plus 1 are 2, 1 plus 1.0 are 2, 1 plus 1 are 2. Replacing one object, which is a symbolic representation of the object, the number 1, with another object that is also a symbol for the number 1, does not disrupt the logic, coherence, or correctness of the operation. In such cases, when different symbols for the same number can be used interchangeably, it is highly likely that operations conducted on symbols representing numbers examine and describe the source objects, that is, the numbers. However, the situation is different in the case of one of the key proofs within set theory known as Cantor's diagonal argument, CDA. In set theory, it is claimed that the CDA matrix examines the elements of the infinite set of real numbers, and consequently that it examines the elements of the infinite set of rational numbers, which is a subset of the infinite set of real numbers. It should be noted, however, that the CDA matrix is unable to accept any of the previously mentioned objects that are symbolic representations of the mathematical object, the number 1, except for one specific symbol, which is intended to be interpreted as an infinite sequence of digits. According to the assumptions of the CDA for real numbers in the range 1, 1, 5, the CDA matrix may look as follows. According to the assumptions of the CDA, we can then attempt to create a so-called new real number from the range 1, 1.5. One of the methods used is to increase by 1 the values of the digits at the subsequent places on the right side of the dot for the consecutive, going down row by row, real numbers in the right column of the matrix. In this case, the new real number would look like this, 1.2311712. This operation cannot be performed for rational numbers represented by a symbol that does not have an expansion in the form of an infinite sequence of digits, an infinite sequence of zeros. The same CDA matrix would then have to look, for example, like this. In this case, to construct a new real number is not possible because for the object, the number 1, represented by the symbol 1, which is in the 6th row of the right column of the CDA matrix, the parameter such as the 6th position after the decimal point is not available at all. It is not available because it is completely unnecessary. The number 1 can be precisely and correctly described, defined, and symbolically represented without any infinite sequences of zeros. Occam's razor rightly dictates in such cases to absolutely reject anything that is not necessary. The source object, the number 1, and any other object that is a number belonging to the infinite set of rational numbers do not possess a qualitative parameter such as an infinite sequence of zeros. For example, the number 1 does not have it on the right side. It does not have it on the left side. Nor does it have it from above, below, or diagonally. An object such as a rational number is not described using an infinite sequence of zeros or any other parameter that is not necessary for the precise and correct description of a specific number with a specific numerical value. Arithmetically, adding 0 to the number 1 any number of times does not change the numerical value of the number 1. The commonly used symbol for the object, the number 1, looks as follows. Adding additional elements, additional qualitative parameters to this symbol, specifically in this case, a decimal point and an infinite sequence of zeros, infinity of sequences symbolized by 3 dots, creates a new symbol, this one. Both of the above symbols share one common parameter, which is the numerical value. From this narrowed perspective focused on numerical value, both symbols can be used as a correct symbolic representation of the mathematical object, the number 1. However, the CDA matrix is unable to accept this symbol, or any of the previously mentioned objects that are symbolic representations of the mathematical object, the number 1, except for one specific symbol. This is because the CDA matrix is not fundamentally concerned with the numerical value of the objects it analyzes, but rather with their graphical, geometric construction. The CDA matrix requires the qualitative parameters of this specific symbol. It needs its infinite sequence of zeros, an infinite sequence of digits, because it examines this specific symbol in terms of its graphical, geometric construction, independent of a parameter such as its numerical value. The CDA matrix does not examine the object, the number 1. It examines another object, and it is specifically this symbol. In terms of its graphical design, the CDA matrix does not examine, nor is it capable of examining, objects such as rational numbers. Instead, the CDA matrix attempts to analyze infinite sequences of digits, which, one must be fully aware, do not constitute valid symbolic representations of mathematical objects such as rational numbers. The CDA matrix tries to analyze infinite sequences of digits that may have absolutely nothing to do with numbers, particularly with rational numbers. The initial attempts to use the CDA matrix by Professor Georg Cantor clearly and unequivocally demonstrate this. In the right column of the matrix, Professor Cantor placed sequences of the letters M and W, which have nothing to do with numbers, especially with rational numbers. I have not exhausted this topic here, but I will conclude at this point before the presentation reaches an discouraging length. I had hoped to be more concise. I apologize. However, from my previous experiences, I know that shortcuts in reasoning do not serve the matter well, as the issues addressed are very complex and small details can be crucial. If you, Professor Penrose, have any questions or doubts, I would be honored to hear them and provide clarifications. These issues are very challenging in many aspects. However, I have no doubt that the end balance of profits and losses from confronting it will be significantly more favorable than the balance in the case of attempting to ignore them. I hope that silence will not be the response from the scientific community, and that silence will not be your, Professor Penrose, answer. Yours sincerely, Adam Polak. P.S. This letter is an open letter. I am sending it in copies to several scientific institutions that should be vitally interested in this topic. It will also be made public on the Internet.